Hi, welcome to this lecture on DC motors. So what is an electric motor? Well, an electric motor is a device which changes electrical energy into mechanical energy, which makes sense. You put electricity in and you get motion out. They're widely used in robotics, toys, appliances, etc. In fact, in whatever room you're sitting in, there's probably at least 5 or 6 items with a motor in it. They use more current than digital logic devices because it requires a lot of current to cause things to actually move. You have to overcome actual physical limitations and actual physical energy things like potential energy, etc., etc. Now, a basic electric motor is a brushed electric motor, and it's called brushed because it has little brushes, is what they're called. So this right here would be called a brush. Now, also inside a brushed electric motor is a permanent magnet with both a north and south pole. And then we have an electric magnet inside that, through a coil of wire wrapped around an iron core, also produces a magnetic core, also produces magnetic poles of south, and the north, of course, would be on the other side. But the electric magnet is electric, meaning that it's connected up to the battery, which is what causes it to get its magnetic pole. Now, you'll notice that where the brushes connect, there's a gap. If you look very carefully here, you can see a gap between the metal. What this means is that as the electric magnet turns inside of the permanent magnet, the gap will cross the brushes and it'll cause the current to invert. So let's look at what happens as that occurs. Okay, so let's say that we have our battery connected up to our electric motor, which the battery is connected to the coil of wire through the brushes that run across these plates with the gap in between. So there's that gap again on both sides. And right now, let's say that our electromagnet has the north pole being here, and our permanent magnet, the north pole is always on top and the south pole is always on bottom. Now, so the battery causes electric current to flow, which causes the electromagnet to have a specific magnetic orientation to it, where the north is on this side. Well, when that occurs, north is going to try and align with the south of the permanent magnet. And the south side of my electromagnet is going to try to align with the north side of the permanent magnet. Hopefully you remember this from physics. So what that means is that this coil, which is on a shaft, is going to spin so that the north can align with the south pole and the south can align with the north pole. So as it spins, it's going to spin to do that alignment. Now, when it's fully aligned, meaning that the south of the electric magnet is lined up with the north of the permanent and vice versa, all of a sudden, the part of the motor that spins is going to disconnect from the brushes because of that gap. When it disconnects, that causes the electromagnet to no longer be a magnet, and the momentum of the movement will continue the rolling until the brushes reconnect on the other side. So the brushes are going to switch from one side of the gap to the other. And when the gaps are on both sides like this, what that does is it means that after the brush connects on the other side of the gap, the electromagnet is now hooked up in reverse of what it was before. So as soon as that happens, instead of the top being south, the top will become north. Well, magnets don't like being aligned north to north and south to south, so this is going to cause the coil on the shaft to continue to rotate, because now the north is going to try to push itself down to align with the southern part of the permanent magnet. And this is going to continue in this cycle of the north pushes down, now we have them lined up, and then the brushes go ahead and cross the gap and change the polarity of the magnet, and it's just going to continue to spin because the polarity of the magnet continues to change every time the brushes cross this important gap. So once again, as it continues to spin, our electromagnet continues to change polarity and we continue to get motion. Right, so here's an example of a simple DC brush motor that you might find inside, say, a toy car. You have the axle of the motor which spins, which provides the momentum to, say, move the wheels on the car. You have the steel can, which is the outside of the motor. You have this nylon plastic cap on the end, and we usually have 2 leads to provide voltage to the motor. That's about it. This is a coin next to it, just so you can get an idea of the size. That overall, these can be made fairly small. So if we take apart the motor, what you can see in here is that on the plastic cap, you can see that we have these two metal contacts on either side that are connected into the power. Well, these are the brushes that we saw in the previous diagram. And then on the actual base of the motor itself, you can see that there's these coils of wire wrapped around, and in the middle of the coils is this big gap. That's the gap that we saw. So these brushes connect onto the coils, which electrify them and create a magnetic field. But when the brushes cross the gaps, it reverses that magnetic field. Well, a basic DC brush motor, like I just described, is actually a really simple device. It's either on or off. It's either powered, which means that you're generating that magnetic field and the motor is turning, or it's not powered. But we want to be able to control it with a bit more detail than just on or off. We want to control things like direction, and we want to control things like speed. So in order to do that, we're going to bring in another component called an H-bridge. An H-bridge is used to control the direction of a motor. And they can control the motor using power electronics, which really just transistors. Hopefully you remember transistors from previous courses. But in case you don't, the basics of a transistor is that you think of it as having a source voltage, a voltage applied at the base, and then an output here. And basically what the transistor says is if you have 5 volts here on the base, then I allow current to flow from the source to ground. If I apply 0 volts, then current doesn't flow. You can kind of think of a transistor as an electronic version of a switch. The difference is if we apply 5 volts, then the switch is closed. If we don't apply 5 volts, then the switch is open. That's an easy way to think of a transistor. So an H-bridge is a device that's made up of 4 transistors that are configured as seen here. That's why we call it an H-bridge, actually. It's because it kind of looks like an H, with the motor in between. The H-bridge has a direction pin that can be set using digital logic highs and lows. And this pin enables or disables the flow of current through the transistors in the correct way. So for example, if we want the motor to turn one direction, we would close this transistor and this transistor, but leave the other two open, which means that voltage would flow from V plus down across the motor and then down into V minus, which would cause the motor to turn that direction. If we set the transistors up in a different way, so that these two are open, or these two are closed and the other two are open, well, then the voltage will flow through the motor in the opposite direction. And the direction that the voltage/current flows through the motor defines which direction it turns. So using this simple 4-transistor design, we can control the direction that a motor spins by controlling what direction the power flows across it. Okay, so here's a sample, slightly more complicated H-bridge circuit that still has our 4 transistors, here, 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 and here, but also has some diodes in there to help protect against some line noise, and a few other things to kind of make the circuit more complete. But the core design is the same, 4 transistors with a motor wired up in between them in that H format. So a classic H-bridge chip is the SN754410, and this is what the pinout looks like of the chip. It's 16 pins. Now this chip has 2 complete H-bridges in it. You have an H-bridge on the left, and you have a full H-bridge on the right. So we're going to take these one at a time. But it actually has 2 full H-bridges or 4 half H-bridges, which is kind of confusing to talk about. But remember, in our H-bridge, looks like an H with our motor in the middle, we have our 4 transistors. Each pair of transistors, so like this pair of transistors where current can flow this way, is half of an H-bridge, right? So there's 4 halves of H-bridges in here. But basically, for any one half of an H-bridge, we have a few important pins. One is the enable pin, which just determines if the H-bridge is going to be active. And then we have an A input and a Y output. Now, the A input, so enable just means whether the chip is on or off. If A is high, then power flows through Y. If A is low, then no power flows through Y. Should be a pretty simple concept, right? Because we're just turning on 2 transistors if it's high or if it's not. Okay, but how do I combine all this together to actually build an H-bridge to control a motor? Well, let's look at how we could control motor design. So I'm going to go ahead and wipe out the right half of the chip here because it's another H-bridge. We're only going to control one at a time. So let's say that we connect up a motor to 1Y and 2Y, which are outputs on either side of the H-bridge. So I'm going to draw kind of a motor here, draw my motor like this. one half of it is going to connect into 1Y, and the other half is going to connect into 2Y. I'm going to connect my enable to just say power, say 5 volts, and pretend that I've connected all my grounds to ground properly, etc., and my VCC here also to power 5 volts. And this is also a VCC, but it's not labeled on here, but that's okay, also 5 volts. Now, how do I control whether or not my motor is going in what direction, etc.? Well, now 1A and 2A are controlling which pairs of transistors are on. So 1A controls one pair of transistors, 2A controls the other. Okay, so if 1A and 2A are both low, then the motor stopped because no current is flowing. If 1A is high and 2A is low, then that means that current is flowing. Let's draw another H-bridge here. Let's say that would cause current to flow this way, which would cause my motor to go forward. Now, if 1A is low and 2A is high, well then that would cause my H-bridge to allow current to flow that way, which means that my motor would spin backward. And then this is the interesting one. If 1A and 2A are both on, well then that means that my H-bridge is actually letting current flow both ways at the same time. So my motor is trying to turn forward and backward with equal amounts of force, which means that it's stopped. Of course, if you actually want the motor to be stopped in your circuit, you should send two lows. Because if you're sending two highs, then your chip is actively trying to drive the motor in two directions at once. It's just not succeeding, which is just going to use extra power that you don't need to. But here's your kind of easy to use diagram for remembering if you wire up a motor this way, how do you get forward, backward, etc., etc. So that helps us control direction, but what if we want to control speed? Well, the way we control speed is by enabling our chip on and off really fast. So remember, we have that enable pin on our H-bridge, which just determines whether or not the H-bridge is in use or not. Well, we could send that enable pin, instead of sending it a constant high or a constant low, we could instead send it pulses with a certain time wave, pulses with a certain period and frequency, etc., etc. When we do that, we call this technique pulse width modulation. And the idea is, by making the pulses occur more frequently or be bigger, we'll increase the average voltage seen by the motor. But if they're really short pulses, then we'll decrease the average voltage seen by the motor. So if we send a PWM signal to the enable pin on the H-bridge, we can alter the speed of the motor, because instead of the motor being on with full power, it'll only be on some percentage of the time, which will cause the motor to appear to move slower. Okay, so the higher the voltage seen by the motor, the higher the speed, which makes sense. In order to manipulate that, we'll manipulate the pulse width modulation duty cycle. You may remember that duty cycle is the percentage of time that a signal is high in a given period. So this one, figure A here, this pulse has overall a very low duty cycle because it's on for a short amount of time, and then it's off for a really long time. So this would be a low duty cycle. Whereas in figure B, we would have a very high duty cycle because it's on for a long time and then off for a very short time. Well, the higher the duty cycle, the more power the higher the average voltage the motor is going to see, and the faster it's going to turn. So if we wanted the motor to go slow, we'd send a pulse width modulation signal with a low duty cycle. If we want it to go high, we'd send a pulse, or go fast, we'd send a pulse width modulation signal with a very high duty cycle. Now, one problem with pulse width modulation is that when we connect it up to a motor, motors kind of act like inductors. And you may vaguely remember that on an inductor, when the voltage changes, it takes time for the current to match that change. So the current ramps up slowly when the voltage increases quickly. Why is this important? Well, if we're changing the voltage quickly using a PWM signal, then the current will take a long time in order to get up. Well, the current is what gives the motor the turning power. So if we use a PWM signal that changes the voltage too quickly, then the motor will never get enough current to turn powerfully enough. This is bad. So in order to solve that, we need to make sure that we have a long enough time that the motor can get up to power. So in this example here, if we have a voltage input that's changing quickly, our current won't change with the nice pretty square wave. It'll look more like a triangle wave as the current gets up and then drops, gets up and then drops, gets up and then drops. And that's not good. So we need to make sure that the period of the signal, which is different from the duty cycle, needs to be long enough for the current to reach an acceptable level. So remember, duty cycle is the percentage of time that the signal is high within a given period. But how long that period is really up to you. So you want a long period. You want to make sure that there's a long period of time between here and here in order to overcome this problem with current not getting up to speed. So you want a long period, but you can still have whatever duty cycle you want within that period. So how do we generate this pulse width modulation signal? Well, frequently a microcontroller is used to generate the signal, but we can also use a 555 timer, which is a very useful thing to do because 555 timers are really cheap. So you can use a 555 timer to generate your PWM signal to turn on and off your motor. Now, another important thing when you're dealing with brushed DC motors in particular is that they produce noise. Noise meaning that it causes your voltage that's on the rest of your circuit to spike and go up and down. So while what you want on a digital logic circuit is a nice steady 5 volts, if you have a DC brushed motor spinning, while you should have 5 volts, you'll really have a signal that looks like this. It goes up and down really rapidly because every time those brushes disconnect and reconnect, it causes a current draw and it causes spikes in your voltage. So that's really not what you want because we have high voltages and currents being switched at really high frequencies. If you get all this noise, you can cause errors in your digital logic chips that happen to share the same power supply. So that's bad. There's a really simple way to deal with motor noise though, and that's to simply add capacitors. So you solder extra capacitors to the motor itself. And you need them at the motor because the closer they are to the source of the noise, the better they're going to do at smoothing it out. So you can use simple 0.1 microfarad ceramic capacitors, and they have to be ceramic because ceramic capacitors are not polarized, so we need non-polarized capacitors. So as an example here, a good way to do it is I could take one capacitor and I could solder it between the two terminals on the motor, just like that. And that would take care of a lot of noise. I can do better and handle noise even better by adding 2 capacitors, one from each terminal. I solder it to the case itself of the motor. Because in most motors, the case somewhat serves as a ground, so we can use it that way. So we can solder 2 capacitors, one each from the terminal to the case. And that'll take care of even more noise than just doing 1 capacitor across the terminals. And last, the best is to use all 3. All 3 would be I have 1 capacitor from each terminal to the case, and then I add an additional capacitor between the 2 terminals as well. So I'd have 3 capacitors on there. And that will take care of almost any noise you're going to get, especially if you have small brushed motors. So let's review. DC brushed motors are simple devices that are either on or off. We use an H-bridge to control the direction, and we use a pulse width modulation signal feeding into the enable pin on that H-bridge in order to control the speed of the motor. And we need to add capacitors soldered to the motor in order to suppress the noise that it produces so that it doesn't cause errors in any digital logic chips that we happen to have in the same circuit. Thanks.